We live in a time where we can actually answer questions about the universe that we see when we look into the night sky. But there are still mysteries that remain to be solved.
SPHEREx and Punch are two completely different missions that are sharing a ride together to space. SPHEREx is a telescope that takes images of our skies in infrared. We're going to take thousands of pictures forming a map of our universe.
We're trying to look back in time to see what happened in the first second after the Big Bang.
Punch is a constellation of 4 small satellites. It's focused on the sun's outer atmosphere, the solar corona, and how that solar atmosphere fills our solar system and bombards Earth's magnetic field.
It's going to be the most complete all-sky survey that we've ever done.
Being able to see basically back in time, that's cool. It's like time travel.
We can expect some surprises in this process.
Together, SPHEREx and Punch highlight NASA's mission to not only explore the cosmos, but to unravel the deeper connections that bind us all.
3, 2, 1, and liftoff.
All right, hello everyone, and thank you very much for joining us live here at Vandenberg Space Force Base in California, where in just a couple of days we have 2 NASA science missions launching together to explore the universe in very different ways. I'm Elise Fisher with NASA's Office of Communications, and today's news conference will discuss the science and discoveries that we expect from the agency's SPHEREx and Punch missions. SPHEREx is a new space telescope that will scan the entire sky to help us better understand the origins of the universe, galaxies, and of the ingredients for life here in our own galaxy. And riding along with SPHEREx is a mission called Punch. Punch is actually a set of 4 small satellites that will study the sun's outer atmosphere to give us brand new insight into the solar wind and its effects on us here on Earth. So with us today to tell us more about these 2 missions and answer your questions, we have a panel of experts. Shawn Domagal-Goldman, Acting Director for the Astrophysics Division at NASA headquarters. Joe Westlake, Director of the Heliophysics Division, also at NASA headquarters. Phil Korngut, SPHEREx Instrument Scientist at Caltech. Rachel Akeson, SPHEREx Science Data Center Lead at Caltech IPAC. And finally, Nicholeen Viall, Punch Mission Scientist at NASA's Goddard Space Flight Center. So we'll hear first some remarks from this panel, and then we will take questions, both from media who are listening on the phone lines, as well as through the hashtag AskNASA. But first, I will turn it over to Shawn Domagal-Goldman to start us off.
Thanks, Elise. I am so excited to be here today to talk about NASA's Astrophysics Next Space Telescope, SPHEREx. And I'm also excited that we're sharing a ride with our colleagues in Heliophysics with their Punch mission. We do things as teams at NASA, and we really enjoy the spirit of collaboration. And so when we can work together across divisions to do things together, that's what we lean into. I also like that because that's to the benefit of the American taxpayer. This is basically two for the price of one. And that's thanks to the folks at SpaceX that provided the rocket that's going to get us there, and inside NASA, the launch services provider team that helped us find that nice ride. I'm going to talk about SPHEREx specifically. I'm really excited for that and what it's going to contribute to the story we tell as astrophysicists. You know, we have the pleasure of really answering three big questions in astrophysics. It's how does the universe work? How did we get here within that universe? And are we alone in that universe? Now, those questions, they're big enough where, and if we could get my chart up, those are big enough where we can't answer them with one instrument. We can't even answer them with one mission. We need a full fleet to do that. And every time we fly a new telescope, we make sure that it adds to that fleet in ways that are unique from everything we've built before. For SPHEREx, the best way I could describe the unique value it gives us is by comparing it to something that's much more well-known, the James Webb Space Telescope. And the way I would describe it is, imagine you're a photographer that wants to capture wildlife in a forest. You may take a camera designed to zoom in on a tree, or maybe even a nest and the eggs inside a nest on a tree. That's what James Webb does. What SPHEREx does is it's the panoramic lens. It's going to give us not that egg in a nest in a tree, it's going to give us the forest and all the trees within it. But for astronomers, the trees are galaxies or other celestial objects, and the forest is the known universe. Now, what SPHEREx is going to do is it's going to tile the whole sky, in fact, 4 times, at multiple colors that you'll hear about later from my colleagues. And when it does that, it's going to get us critical information about galaxies throughout that sky at various points in the universe's history through a critical epoch of the universe's history and the evolution of galaxies within. By getting that much data, it's going to be able to do something else that's kind of magical, which is it's going to understand further back in time. If you can imagine an explosion happening and all the little bits and pieces flying out from it, if you get really good information, you might get some information about that explosion that happened at the center. SPHEREx is going to do that too. It's going to get reverberations from the Big Bang. In fact, fractions of a second after the Big Bang that echoed into the eras that SPHEREx is going to directly observe. Now, as it does that, it's also going to provide us our first infrared spectroscopic survey of the night sky and everything within it, not just the galaxies I mentioned, but stars and quasars and planet-forming regions. And for me as an astrobiologist, one thing I'm very excited for is it's going to give us a full sky map of ices, waters, and other ingredients that are essential to life, which connects the question of how did the universe evolve and how do we get here to where can life exist and are we alone in that universe? And I'm excited for all of that and even more because we're going to take all that data and release it to the public so that the best minds in the United States can find other uses for the data that we haven't even imagined today. Now, that's all thanks to a huge team of people, in fact, a team of teams. I mentioned our colleagues at SpaceX that are getting us safely to space with launch services provider here at the launch services provider team here at NASA. I also want to give a shout out to our colleagues at JPL that led that mission. And let me just pause. This is a team of teams. The JPL team did a fantastic job for years managing everyone else I'm going to mention and getting us to the launch pad. They also did it the last 2 months under tremendous personal stress from the wildfires in California. So both at the team and at the individual level, I am deeply thankful to all of them. The team that they managed included a bunch of other partners, including BAE Systems. They're the ones that made the telescope and the spacecraft bus. The IPAC team that's going to house the data and all the beautiful bits that we're going to get down from that spacecraft. Our partners at KASI from Korea that have provided a test chamber for us to use to test this out properly, and from Caltech. That's where our PI sits, Jamie Bach. He led a team of people from across the United States at multiple institutions that are going to be analyzing the science data. And lastly, I want to thank my colleague to my left, your right here, Joe, who we worked with to make sure we could fit Punch and SPHEREx in the same vehicle. So that's thanks to both our divisions and our bosses at the Science Mission Directorate at NASA. So that's why I'm excited to be here. I'm excited to partner with Joe, your team, and I think I'll hand it over to you to talk a little bit more about Punch.
Oh, yeah. Yeah, thank you so much, Shawn. Yeah, we're really excited to be on board for this. You know, Heliophysics is catching a ride, going along with the SPHEREx launch, and really, you know, providing over and over again that value to the American taxpayer, having these two missions go up together. Punch is the newest Heliophysics addition to the NASA science fleet. We're delivering science every second of every day in a way that only NASA can. Punch fills in that science puzzle between the sun's outer atmosphere, the corona, and the Earth. And Punch is going to actually take that image and really be able to observe everything that's going on in between the sun and the Earth. Heliophysics is really that science that spans the entirety of our solar system. You know, we talked about, you know, the forest, viewing from different cameras and different images, viewing the entirety of the galaxy. We're viewing our star, our sun, with Punch. And heliophysics is spanning that entirety of the solar system, its whole expanse out into the farther solar system, into the heliosphere. So Punch is joining this heliophysics fleet of missions that study all the elements of this system. If you could bring up the next image. So in December, the Parker Solar Probe actually made its closest ever approach to the sun and survived. This is the first of many, several visits that it will make. That's the closest in. That is the closest in to the sun that we have ever been, and for now, will ever be. Heliophysics also manages the Voyager mission, the farthest out that humanity has gone physically out into the solar system. These two together are the expanse within which we have heliophysics. But we're adding more explorers to this fleet throughout 2025 and beyond, with 5 more NASA heliophysics launches in this next year. And I'm going to tell you about 2 of them coming up. After the SPHEREx and the Punch launch gets off the ground, most everybody else on this panel is going to take off, head back home, and continue and hopefully be seeing amazing science data, be seeing the amazing images that are going to come down from both. The heliophysics team is going to stick around, and we're going to actually launch the next mission, EASY, on the next transporter launch. If we could call up that next image. EASY is a mission made up of 3 small satellites that are going to study the auroral electrojets, which are the currents between the Earth's upper atmosphere that drive the aurora, and they create the circuit between what happens in the space and the effects on the Earth. That data connects the puzzle of what we're looking at with Punch, from the sun to the Earth. And that puzzle helps us to understand and better predict the space weather that affects us here on Earth. And then later this year, if we could call up the next one, we'll be watching as the Interstellar Mapping and Acceleration Probe, the IMAP mission, which will connect further the sun to the Earth at the Sun-Earth L1 point. This strategic mission is studying that interface between the sun and the Earth, and then also studying how it actually inflates out the whole of the heliosphere by mapping that interstellar structure or interplanetary structure of our heliosphere. Really excited to see that. And IMAP, similarly to what we're doing with SPHEREx and Punch, will be providing that great value that gets from the rideshare program. It'll be carrying along with it the Carruthers Geocoronal Observatory, as well as a NOAA space weather mission, the Space Weather Follow-On. Rideshare capitalizes on every kilogram of launch capability sent up to space, and we do that because these launches are unique opportunities for us to get our science into space. It's a really busy year for us in heliophysics. I'm super excited to be here. I'm super excited to be here with my colleagues from astronomy, from Shawn, from others. And I'm really excited, and I just can't wait to see what's going to come from SPHEREx and Punch. So with that, I'm going to turn it over to Phil Korngut, who's going to tell us more about SPHEREx.
All right, thanks, Joe. So SPHEREx is going to produce an enormous 3-dimensional map of the entire night sky. And with this immense and novel data set, we're going to address some of the most fundamental questions in astrophysics. If you can bring up my first animation, please. So SPHEREx stands for the Spectro-Photometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer. It's a space telescope operating in low Earth orbit, and using a technique called linear variable filter spectroscopy, we're going to produce 102 maps in 102 wavelengths every 6 months. And our baseline mission is to do this 4 times over the course of 2 years. Now, within this framework, we've optimized SPHEREx to tackle these three big questions that Shawn introduced earlier. I'm going to address the first two, and I'll pass it on to my colleague Rachel for the third. First, SPHEREx is really trying to get at the origins of the universe. What happened in those very few first instants after the Big Bang? The reigning theory that describes this epoch is called inflation. And as its name posits, it proposes that the universe underwent an enormous expansion, going from smaller than the size of an atom, expanding a trillion fold in just a tiny fraction of a second. A theory like inflation is actually needed to explain lots of the observations we have, particularly from the cosmic microwave background, because it answers questions such as why is the universe uniform on the largest scales, and why is its geometry spatially flat? So if you'll bring on my next image, please. This image is from a ground-based pathfinder called DESI, and in this image, every single dot you're looking at is a galaxy, each with hundreds of billions of stars. And what you'll notice in this is that the distribution is not random. It's highly structured. It's clumped together in what we call the cosmic web, and it has little filaments in it and voids. The origins of those fluctuations are actually very profound and can tell us about the early universe. If you'll bring on the next animation, please. Just after the Big Bang, when the entire universe is smaller than the scale of an atom, it's governed by quantum mechanics. And that arises these quantum fluctuations, little overdensities and underdensities that expand and grow with the universe as it cools. That's where the first stars and galaxies will form in these overdense regions. So that means if we can produce a map of what the universe looks like today and understand that structure, we can tie it back to those original moments just after the Big Bang. So the largest scales imaginable on billions of light years across are tied to the smallest scales imaginable, just a tiny fraction of an atom. Our next science theme is to understand the history and the evolution of galaxies. Now, the classical approach to doing this is through deep studies with mighty telescopes like Hubble and James Webb. If you'll bring up my next image, please. So this is the Hubble Deep Field. It's a very famous image. It's very small on a side, but you can see it reveals a tremendous amount. And we've learned so much from these kinds of studies. But fundamentally, there's always more that's missing from these because there are always galaxies which lie beyond the detection threshold. This is also insensitive to large diffuse structure. So SPHEREx takes a different tack. And what we study is a signal called the extragalactic background light. And what we're doing there is instead of identifying individual little objects, we study the total integrated light emission that comes going all the way back through cosmic time to that first dawn. And we do this by making large format maps. If you'll bring up my next image, please. Here's a prototype that's done with the Spitzer Space Telescope. This is now a few degrees on a side. And if you take that map and you mask out all the stars and galaxies that you'll see, and you look at what the fluctuating light field looks like beyond, that's this puffy image that you're looking at. And that's the extragalactic background light, and it contains a wealth of information from every light source that's ever existed. So what we're going to do with SPHEREx is to map that in 102 wavelength bands in the near infrared, on a large hundreds of square degree chunks near our ecliptic poles. And by cross-correlating all of those maps, we can tease out the various components which comprise that and harvest that wealth of information that the extragalactic background light possesses. So on a personal note, while these two science themes I think are among the most compelling that we have in astrophysics, and I've certainly wanted to dedicate my career to the study of them, I think that the most exciting thing that's going to come out of SPHEREx is something that we haven't even thought of yet. When you offer this amount of information out, there could be someone sitting in high school now who's going to pore over this data in years to come and just find something that's truly amazing. So I'm unbelievably excited for this mission to launch. And to tell you about our other science themes, I'm going to introduce my colleague, Rachel Akeson.
Thanks, Phil. SPHEREx will map the origins of water and ice across our galaxy and allow the astronomy community to pursue their own studies of billions of stars and galaxies. Let's start with one of the biggest questions we have about our universe. Where is all the water? On Earth, we know that every living creature needs water to survive, but how and when did that water get here, and how might that work for planets around other stars? SPHEREx is going to help us find answers by investigating the origins and abundance of water and ice across our galaxy. To do that, the observatory will focus on collections of gas and dust called molecular clouds. If we could have the first video, please. What are molecular clouds? These are clouds where disks of gas and dust collapse to form planets and stars. Within these disks, like the one represented here, molecules such as water and carbon dioxide can exist both as a gas or as ice on dust grains. We think that most of the water and ice in the universe is in places like this. It's also likely that the water in Earth's oceans originated in a molecular cloud. So how will SPHEREx map the ice in our galaxy? While other space telescopes have found reservoirs of water in hundreds of locations, SPHEREx observations of our galaxy will give us more than 9 million targets, a much bigger sample than we have now. If we can go to the second animation, please. As Phil explained, SPHEREx will make over 100 measurements of each point in the sky at different infrared wavelengths. Here's why that's important. Every molecule, such as water or carbon dioxide, absorbs light at different wavelengths. We can think of this as its spectral fingerprint. So by measuring how much the light changes across the wavelengths, we can see how much of each molecule is present. If we can have the next animation, please. SPHEREx will look for these spectral fingerprints, like dark notches in the light from millions of stars within our galaxy. And you can see these dark notches here in the diagram. This will include stars that have only just been born and those that are hiding behind the dark molecular clouds where stars are created. Together, all these fingerprints will tell us how much of each molecule is present in these different locations. As water is essential to life here on Earth, knowing the water content around the galaxy is a clue to how many locations could potentially host life. And finally, we have the SPHEREx catalog. In addition to the 3 science goals that Phil and I discussed, there are many more science areas that SPHEREx will impact. If we could have the next image, please. SPHEREx will create a map of every point in the whole sky at 102 different wavelengths. This map will include billions of objects, from asteroids and comets in our own solar system, to stars across the Milky Way, to galaxies far from us, like this one, the Whirlpool Galaxy, shown here in 4 different wavelengths, including in the infrared, where SPHEREx will look at it. Images from SPHEREx will be available at the NASA IPAC Infrared Science Archive and will allow scientists from all over the world to study the composition of their favorite objects. Last month, when I was at the annual meeting of the American Astronomical Society, many people came up to me and told me how excited they were that SPHEREx was about to launch. Well, our whole team is really excited too, and we're looking forward to seeing all of our hard work make it into orbit and to making all of this new and unique data available to the community. And with that, I'll hand it over to Nicholeen Viall to tell us about PUNCH.
All right. So PUNCH stands for Polarimeter to Unify the Corona and Heliosphere. PUNCH is a NASA mission in low Earth orbit. It is comprised of 4 suitcase-sized satellites. And together, they piece together the 3-dimensional global view of the solar corona, the sun's atmosphere, as it turns into the solar wind, which is the material that fills our whole solar system. Could you play the video, please? So the PUNCH mission advances the science of heliophysics, which is the study of the sun and the sun's domain and how the sun influences the solar system. And we do that by imaging the sun's corona and the solar wind together. The PUNCH scientists hope to better understand the entire inner solar system, from the sun through the corona out into the inner solar system, and how that material impacts Earth, and to do that as a single connected system. During a total solar eclipse, we get to see the solar corona, the atmosphere of the sun, because the moon blocks out the main body of the sun, allowing us to see the much dimmer corona around it. PUNCH does this all the time. PUNCH makes artificial eclipses by blocking out the main body of the sun so that we can always see the corona. And it does this with an extremely wide field of view, so that we see not just the corona that you get to see during a total solar eclipse, but also that corona as it expands out through the whole inner solar system and becomes the solar wind. It does this by using 2 different types of instruments. The first type of instrument is called the narrow field imager, And it is one of these artificial eclipses that blocks out the main body of the sun so that we can see the corona around it. The second type of instrument is called the wide field imager. The wide field imager makes an artificial horizon so that it can look far away from the sun at the very faint solar wind that is constantly bombarding the Earth. By combining the NIFI instrument and the WIFI instrument, all four of those spacecraft together piece out this enormous three-dimensional, 360-degree view of the solar system. And so in this way, Punch is able to take high-resolution images and combine that with their global viewpoint. The Punch mission explores the formation and evolution of transient space weather events too, like coronal mass ejections. These can spark strong space weather events like the aurora that Joe mentioned earlier that EASY is going to study. Current instrumentation can view coronal mass ejections, but it can't follow them all the way to Earth, and it can't follow them with the kind of resolution that we need to be able to see to understand which part of the CME, which part of the coronal mass ejection is actually going to impact the Earth. With Punch takes advantage of polarized light to actually understand the direction that that coronal mass ejection is moving, whether it's coming towards us on the Earth or whether it's heading to the side. And this polarized light, it's very similar to your polarized sunglasses. This mission will also shed new light on shock waves. Oftentimes these coronal mass ejection cause shocks. Those shocks take benign particles and accelerate them up to energetic particle radiation, which can endanger our spacecraft and our astronauts. Punch also reveals the daily space weather, and this is the part that I'm so excited about. The sun is never quiet. The way that the sun makes the corona and makes the solar wind, it's constantly having little explosions. So even when there's not a big space weather event, even when there's not a big CME, there's still little events that constantly bombard our Earth. Punch is the first instrument to have the sensitivity and the resolution to be able to see that daily space weather so that we can really understand this low but constant impact on our Earth system. Lastly, Punch really exemplifies the unify in our name because we are providing the global context for all of the other heliophysics missions that are flying in the inner heliosphere and also looking at the impact of these space weather events on the Earth. And so I'm so excited for the Punch launch.
Great. Thank you so much, Nicholeen, and thank you all for those comments. And with that, we will go ahead and begin taking your questions. So for media who are listening on the phone lines, you can press *1 to enter the queue to ask a question. And our first question that we'll take on the phone is from Gina Senseri with ABC News. You can go ahead, Gina.
How do we sum up for our viewers who might feel a little overwhelmed when you start talking about the beginning of the universe?
Great, thank you, Gina. So, Phil, would you like to jump in on that one?
Well, yeah, I mean, I think a good boiled down is really just the concept of mapping the large-scale structure of the universe and, just the amount of information that's going to be present in a humongous data set like that is tremendously powerful. Addressing the early universe and kind of the origins of everything is one of the applications we take from that. But it's a lot. There's a lot that can be just gleaned from that data set. So I would emphasize just the grandiosity of the largest map you can think of.
Great. Thank you, Phil. And as mentioned, we are also taking questions from social media using the hashtag AskNASA. So we do have a first one of those. This is from Olivier Vortex on X, and he asks, the SPHEREx and Punch missions are groundbreaking. What new technologies are being developed for these studies? So perhaps, Phil, if you'd like to jump in on SPHEREx and then Nicholeen on Punch.
Yeah, so the technology that we're employing on SPHEREx, I think, is a great solution to this type of problem. We use what's called linear variable filters over our detector, so you can think of, those are our eyes at the camera, and we place over them these tiny little several grams of sapphire which have special coatings on them. And those enable us to build up this spectral data cube. And I think other more traditional types of spectroscopy, if you wanted to survey the whole sky, would be extremely massive and therefore costly in orbit. We'd need fiber bundles and things like prisms or dispersion gratings and things like that. So I think that's a really good way to go at it. I would also emphasize that SPHEREx, while we're in the infrared, it's absolutely essential to be cooled down to very low temperatures. Our detectors are at 45 Kelvin, which is around minus 350 Fahrenheit. And we do this without the use of any refrigerators or liquid cryogens, and we actually use a passive radiative technology that uses the coldness of deep space itself to dump our power out. So I think we've architected a really good, efficient, and novel technology solution to this problem of making a spectroscopic map of the entire sky.
Yeah, and for Punch, we're really standing on the shoulders of giants. The new technology is actually learning from our previous missions and combining different pieces of technology that had never been combined before. So stereo has looked in polarized light and has looked at the whole inner solar system, but not with this kind of resolution, not even close. We're doing 100 times better than what stereo did, and we're going and looking over the poles, and that required tremendous amount of sensitivity. SOHO also building off of what we've learned from those previous missions and combining existing technology but in a new way so that we can really combine both the high sensitivity with the global mapping.
And I just want to zoom out. I think when it comes to technology development, what you're hearing are strategies that we take on so that we make sure that we identify which technologies are needed, which ones aren't needed, and then the ones that are, we focus on early in the life cycle of a mission so that we keep that whole mission on schedule and budget. And that's something that we've gotten really good at over time. And that's something that we're applying not just to the missions you're hearing about today, but across our fleet, especially for me coming from astrophysics. We've applied that to the Nancy Grace Roman Space Telescope, and we're now starting up a major technology effort for the Habitable Worlds Observatory, which is the next flagship to follow Roman.
Great, thank you all. Our next question also comes from social media, and this one is for Joe. So it asks, how is the Punch mission different from the Parker Solar Probe?
Yeah, so Punch is observing here at the Earth, right? It's observing the sun, and it's observing how that solar wind is connected out to the Earth. It's giving us that global view of the solar wind as it comes out. Parker gives us a snapshot, right? Parker is diving into the solar wind, diving into the solar corona very rapidly, very fast to get that instant knowledge, the knowledge of what's going on in the solar wind as it is created, as it's generated, as it comes out. And so the two of them together can give you that global picture. It's like a microscope and a telescope together, right? You're witnessing the global view from Punch, the telescope, and you're watching and you're assessing each particle or each parcel of solar wind as it goes out, the microscope with Parker Solar Probe.
Thank you, Joe. Our next question is from msadra1010 on Instagram, and they ask, how many years will it take for SPHEREx to complete its maps? So maybe either Phil or Rachel, whoever would like to jump in, could you talk a little bit about that timeline and then about the process of making that data available?
Sure. So as Phil mentioned at the start, SPHEREx is going to survey the entire sky every 6 months, and we have a 2-year mission, so we'll get 4 surveys of the entire sky. In addition, at both the north and south poles of the sky, we'll get much more detailed maps, many more images. And so these images will be available to the community starting very soon. We'll just need to build up to get the whole sky. So every 6 months, we'll get the whole sky, and we can start science as soon as the images start being available.
Great, thank you. We have another question. This is from Matthew on YouTube. It's for you, Shawn, and a little bit similar to the question that we got for Joe. Is SPHEREx very different from are missions like Hubble, Spitzer, James Webb, or Euclid?
Yeah, I think, and I'm going to look to my colleagues to check this as I say it. I would say it's most similar to Euclid of the missions we've flown before in the sense that it's a survey. I think what I'm excited about is we are now entering an era where we are looking at more surveys of the full sky. SPHEREx is a part of that story in the infrared in particular. That's also something the Nancy Grace Roman Space Telescope, which I mentioned before, is going to do in a different way and in a complementary way. So I would say if I were to compare and contrast, I would say SPHEREx is the infrared survey we're doing now. That's going to be followed by Nancy Grace Roman, which is also going to do an infrared survey, but it's going to see deeper into the universe's history in terms of what it's able to directly observe. And I think those are the ways that those two missions complement each other. I don't know if either of you want to add anything to what I said.
I think that's a great summary. And I think that they are, just to go one step further on the complementarity, Euclid is also studying the large-scale structure of the universe, but they're looking at a different epoch kind of further back, ironically, to learn more about the universe today because of the dark energy. And it's easier if you want to learn about dark energy today, you want to look further back at the large-scale structure before dark energy took over. SPHEREx is looking at the large-scale structure of the universe today and trying to go all the way back to those initial conditions. So it's complementary on that kind of scale, and Nancy Grace Roman will also contribute on that. And again, it's just a literal scale complementarity because SPHEREx, our real strength is that we have a tremendously stable platform from space, and we're surveying those largest modes. So that's really hard to do when you build telescopes like James Webb or also Roman that are designed to really resolve fine detail. It's extremely hard to do that on the large scales as well. So you need this complementarity, something that's enormously large and something that gets enormous detail.
All right, thank you. We'll take our next question. This is from Mavis Kilpatrick's on YouTube, who asks, is Punch going to have any means or ability to see or study solar flares? Perhaps a warning for a large, potentially damaging solar flare. So, Nicholeen, would you like to take that?
Yeah, Punch will see the result of some solar flares when they burst out and create a coronal mass ejection. But not all solar flares do that, and we don't look low enough down to see the solar flare itself, which is the bright light that happens from the magnetic explosion on the disk of the sun. But in concert with our other heliophysics suite, like Solar Dynamics Observatory, we can piece together when those solar flares do turn into a coronal mass ejection, and we can piece together everything from the disk of the sun through the inner solar system all the way to impact at Earth.
Thank you. Our next question is from Ethan Wu on X, who asks, I'm curious, how many galaxies have we estimated there are so far? So as we talk about SPHEREx looking at that collective glow of galaxies, Phil, would you like to jump in?
Sure, yeah. So in the causal connected universe, so the universe that we have accessible to us, there's of order, 1 trillion galaxies. SPHEREx is going to survey spectroscopically hundreds of millions in our prime survey. There will be much more in there, but the ones that we get those three-dimensional positions for is on the order of hundreds of millions, like 500 million.
Thank you very much. Let's see, our next question here. I know you've all touched about on this a little bit, but maybe we can elaborate. Moon to Mars Quest on X asks, will the images and data sets be available for public access? So Rachel, would you like to jump in for SPHEREx?
So I'll start off with SPHEREx. So the SPHEREx images will be available at the Infrared Science Archive, and they are in standard formats and so available to anyone in the community. Although SPHEREx project itself doesn't have any citizen science projects, they will be available for those. People who want to access them can go to the website that was listed earlier and find links down to the data. And I'll turn it over to Nicholeen for Punch.
Yeah, Punch hosts its data through NASA, and the second that the data are calibrated and usable, the entire world will get those data at the same time that our science community gets them. And we will have both quick look products, which would be more appropriate for forecasting, and we also have the scientific quality data, and that goes out to the entire world.
All right, great. Well, thank you all for those responses. Thank you for taking some great questions from social media. Before that we wrap up, I think we would like to hear from each of you, each of our panelists, in terms of what you are most looking forward to about these missions, or what you might be proudest of after having worked on these missions for quite some time. So, Shawn, I'll start with you.
So mine's going to be like super personal. This is the first time I'm going to be like, as we say, on console or in that like mission control room. So like that's on a personal level, that's super cool. If I'm zooming out, I would say the fact that we're inserting SPHEREx into this sort of era of survey telescopes, both domestically with what we're leading from NASA and as you heard before, what we're partnering with internationally with Euclid. So I think those are the two levels I would answer that question.
Yeah, with Punch and this launch that's coming up, I'm really, really excited, having experienced the eclipse last year. I hope you all had an opportunity to go out and see that. You were able to see with your own eyes the upper atmosphere of the sun, right? With Punch, we're going to be able to see that so much better and see so much more of the structure as it comes out to the Earth. I think as this thing that we've thought of over and over again as being empty space, big empty space between the sun and the Earth. Now we're going to fill it. We're going to understand exactly what's within it and be able to see that on a constant basis. So really excited for the data that's going to come down.
Yeah, so I think on the near term, I am just so unbelievably excited to get my hands on those first images that we get down from SPHEREx. I've been working on this mission since 2012 as a young postdoc, and the journey that it's taken from those, conceptual designs to here, it's on the launcher, is just so amazing. And when I'm actually looking at that data, it's going to be so unbelievable. And then going a few years down the road when we've actually harvested that information from the large-scale structure, and when I'm looking at a plot that maybe we can learn something about the fundamentals of the origin of the universe that we just haven't had access to before, that's just going to be just totally mind-blowing, and I am just so excited.
So it's a very exciting time in astronomy missions for SPHEREx to be launching. As we've told you, we're going to do this great all-sky survey. But then there are all these other great telescopes like Hubble and James Webb that we can follow up. So we can learn about new objects or interesting objects at SPHEREx and then follow up with these other great telescopes. And like Phil, I've been working on SPHEREx for a long time, and it is so exciting to be here with the team and actually see everything. All the PowerPoints are now worth it.
All right. Well, I think Punch is going to revolutionize our physical understanding of space weather events and how they propagate through the inner heliosphere on their way to the Earth. And that is true, I think, both for the big space weather events, the big CMEs, and also this daily driving. We're going to have physical understanding that we've never had before after Punch.
All right. Well, thank you all so much for those comments, for participating here, and thank you very much to everyone who joined us. We really appreciate your questions. If you would like to learn more about these missions and continue to follow along with them, you can visit nasa.gov/SPHEREx and nasa.gov/punch. And of course, please don't forget to tune in to watch our live broadcast of this launch on NASA Plus. SPHEREx and Punch are targeted to lift off no earlier than this Friday, February 28th at 10:09 p.m. Eastern or 7:09 p.m. local time. So thank you again for joining us.